Okay, so we've covered 3 of the 4 ways of calculating delta H. The first one was delta H of combustion. The second one was delta H of formation. The third one was using average bond enthalpies, and now we're going to do Hess's law. Hess's law states that regardless of the multiple stages or steps of a reaction, the total enthalpy change for the reaction is the sum of all changes. What that means is that reactions don't happen in one step. For example, here you have the overall reaction is the one at the top. N2 plus O2 makes 2NO2. But it doesn't happen all at once. The second, where it says given, they give you the 2 steps for that reaction to happen. In the first one, the N2 reacts with the O2 to form 2NO, and the enthalpy, the delta H for that one is positive 180 kilojoules per mole. For the second part of the reaction, it's 2NO plus O2 makes 2NO2, and that delta H value is negative 112. Okay, so to do this, basically you just need to figure out how to add up the equations so that they end up with the overall equation. So this is what I want. So look at what I'm given. I notice that I want N2 to be on the reactant side. So since I want N2 to be on the reactant side, this one should stay the same because N2 is already on the reactant side. Notice that N2 doesn't show up anywhere else. So leave that one alone. Rewrite it. N2 plus O2 makes 2NO. For the second reaction, I notice that I want 2 NO2s on the product side. Again, the second reaction has 2 NO2s on the product side. So I'm going to leave that one alone and I'm going to rewrite it. 2NO plus O2 makes 2 NO2. So what you'll see is that if you look at the reactant side and the product side, anything that shows up on both sides, you need to cancel. So that 2 NOs and 2 NOs cancel. And what are you left with? N2 right here plus 2 O2 right here, because there's 2 of them, right? 1 plus 1 is 2. And then 2 NO2. So what do you have? N2 plus O2 equals 2 NO2. And that is the overall reaction that we wanted. So since we didn't have to do anything to these reactions except for add them together, then we just add these 2 values together. Positive 180 minus 112 gives us a positive 68 kilojoules per mole. So that's the delta H for the entire reaction. For our second example, we have 2NO plus O2 makes 2NO2. Here's the 2 steps of that reaction. This one's a little trickier because you actually have to manipulate it a little bit. Okay, for example, notice that we want the 2 NOs on the reactant side. And here, the 2 NOs are on the product side. So I'm going to flip this whole reaction. So I flipped it in orange. I put the 2 NOs on the reactant side and the N2 plus O2 on the product side. If I flip the reaction, I have to change the sign. It is no longer going to be positive 183. Now it's going to be negative 183 kilojoules per mole. For the second reaction, okay, the problem there is that overall I want to have 2 moles of NO2. And this one only has 1 mole of NO2. So I'm going to take this entire reaction, including the delta H, and I'm going to multiply it by 2. So I did that here in brown. I'm going to multiply everything by 2. And multiply the delta H by 2. So in the end, what that leaves me with is 2 NO. 2 times a half is 1 N2. 2 times 1 is 2 O2s. On the product side, we have the N2 and the O2 from the first reaction. And then remember, the 2 multiplies to the 2 NO2. So I have 2 NO2. Can you guys see that? NO2. All right. And then, of course, I had to multiply by 2 here as well, which gave me positive 66. So I had to flip the first one, multiply the second one by 2. And what that did is that you can see now, look, 2 NOs, it doesn't show up on the other side. N2 does show up on both sides, so those cancel out. This one, there's 2 O2s on this side and only 1 on this side. So this is going to cancel out 1 of these. So what does that leave me with? 2 NOs plus 1 O2 forms 2 NO2. And that's what I wanted up here. Two NOs plus O2 makes two NO2s. So now I take the delta H that I flipped to negative and the delta H that I multiplied by 2 to get positive 66 and put those together, and that gives me negative 117. Okay? So sometimes you have to multiply by a factor, sometimes you have to flip it. Basically you need to overall get the reaction that they give you. Now, one thing to remember and notice is that anytime you have a negative delta H value, that's going to mean that that was an exothermic process or reaction. Anytime you have a positive delta H value, that's going to indicate an endothermic process or reaction. The next part of the lesson, so that's Hess's law. So we've covered all the 4 ways of calculating delta H, okay? So you're going to be practicing some delta H by Hess's law. You'll be doing that. That assignment will be posted next. This part here is review, sketching and evaluating endo and exothermic processes. Again, we just talked about how delta H, if it's negative, it's exothermic. If delta H is positive, then it's endothermic. And then you need to be able to sketch out the diagrams. So this is a review from last year. Okay? So you guys know that if the products have a lower energy level than the reactants, as in the first graph, then it's exothermic. So see, the product's energy is higher, and then after the reaction, the product's energy is lower. That means exothermic, because this amount of energy right here, the red line, that's how much energy was released. For the other reaction, or the other graph, notice that the reactants are lower in energy and the products are higher in energy. So the energy for that to happen, it required energy. That red section is the energy absorbed. The amount of energy was required to take for this reaction to take place, and that is the graph for an endothermic process. A couple more things here in the last part of topic 5. We're going to go ahead and finish the notes, going over the notes. Bond strength in ozone, O3 compared to O2. Bond order in ozone is 1.5, and that's because of the delocalized pi bonds. We'll talk about that in a bit in the next picture. And then oxygen gas, which is O2, has a bond order of 2 because of the localized double bond. Localized means that the electrons are not going to move. Delocalized means that the electrons can move. Delocalized, like right now, we cannot delocalize from our houses, right? We have to stay localized in our houses. We can't move, okay? So ozone is going to be more prone to decomposition because of that lower bond order. So I can show you through these pictures. Here is resonance forms of ozone. So ozone, remember that the double bond can be here and the single bond here, or the single bond here and the double bond here. These are both valid structures of ozone. As a matter of fact, you should write them both when you're talking about resonance forms of ozone. But this is a pretty cool part that you can actually write it like that. You see that dotted line? That dotted line is saying that the double bond can be at either place. And that means that the electrons can move, and that means that they're delocalized. So the bond order is 1.5. Watch. 1, this counts as 1, and this is 0.5. So 1.5. Whereas with oxygen, I'll draw that real quick right here. I want you guys to add this. Oxygen gas. Add this to your notes, please. It's just O, double bond O. Those electrons don't move. That's the only way that those electrons are going to be arranged. So the bond order is 1, 2. Okay? So this bond order is 2. This bond order is 1.5. And therefore, that makes ozone more easy to break down, which is the skill that they want you to know. Okay, ozone is more prone to decomposition. And that's topic 5.